you will notice that I've arranged this so that this is the second part of section 4.3 in your textbook, and it's the first part of section 4.4. And that's because, I mean, it's treated differently in 4.3 and 4.4, but what we learn at the end of section 4.3 is the same thing that is taught at the beginning of 4.4. They're the exact same types of questions. And what we're doing here, everybody, today is solving basic trigonometric equations. What do I mean by a basic trigonometric equation? I mean one that's not quadratic. So what we're going to be looking at on Monday is solving equations that have trigonometric expressions in them, but also happen to be quadratic at the same time. These are, if you want, trigonometric linear. Okay? Trigonometric linear. Just so that, because I can see some of your eyes darting around wondering what I'm talking about. This is an example of a linear trigonometric equation. This is an example of a quadratic trigonometric equation. And by the way, I might as well get this out of the way. We would not write it this way, we would write this. And this is pronounced sine squared of theta, and it means sine of theta quantity squared. But what I'm saying as an introduction here is that this is today, and this is next week. Okay. So let's get started. Consider this statement. It is an equation, but it's also a statement. Sine of theta equals 1/2. Show that 30 degrees is a rotation angle that makes this true. This is not a Math 30 level question I'm asking. There's a number of ways we could do this. One of the things you could do is just blindly take your calculator, make sure it's in degrees, and go sine of 30. Yep, makes it true. I would hope that at this level, you should be able to reason out that it's true because 30 degrees is here on the unit circle, and the coordinates of that point are √3/2, comma 1/2. So, I mean, sine of 30 degrees, this is 30 degrees in here. Sine of 30 degrees is the y coordinate. I don't think you need a calculator here to know that sine of 30 is 1/2. Show that 150 degrees is also a rotation angle that makes it true. Well, if I take a look at 150 degrees on the unit circle is the 30-degree mark away from the x-axis in quadrant 2. This is theta this time. And we take a look at the coordinates here, and they are negative √3/2, comma 1/2. So what would sine of 150 degrees be? Well, it would be the y coordinate. And I'm building up to something. I'm just laying a very solid foundation for what's about to come. I want to ask you to think about a question that's not actually in your note package for this warm-up. And it's this. Forget about angles. Will there be any other places on the unit circle other than those two that have sine values of 1/2? Well, there can't be, because as soon as you move away from those two positions, maybe you're going to look higher, your x-coordinates are going to be greater. And as soon as you go lower in terms of a reference angle, the y-coordinates will be different as well. So there are only two locations on this whole rotation idea that have sine theta values equal to 1/2. But are there other angles that would have sine of theta equals 1/2? Can somebody give me another angle other than 30 or 150 where sine of theta would still be 1/2?
390.
390. How'd you get that?
Add 360 to 30.
Right. So you're still landing in this same location. You're just saying, well, I'm going to go around 360 plus another 30. This is back to the whole trip being different, but the destination is the same. There are only two destinations here that have that sign value. C, do all rotation angles coterminal with 30 make the statement true? Well, this is just what we were getting at. Alex said 390 makes it true. And by definition, if it's a coterminal angle with 30 degrees, it's the same location on the unit circle, so it's the same y-coordinate of a half. Will every coterminal angle with 150 make it true? Yes, for the same reason. Coterminal means same termination point. So the answer to this is yeah. And I guess what I want you to understand just initially is that when you look from 0 to 360, or 0 to 2 pi if you like, we have two solutions in that limited domain of angles, but there are in fact an infinite number of solutions if we broaden our horizons and look at any rotation angle. Write the general statement to describe all angles that make the statement true. So if I said to you sine of theta is 1/2, what is theta? Well, theta can be 30 degrees plus 360 degrees times n, where n is an integer. Do you remember talking about coterminal angles and I said we shouldn't use integer because it includes negative? Well, if we wanted negative, I guess we could include it, but we shouldn't use it because it includes 0. And 30 degrees is not coterminal with 30. That's not what we're talking about. Is 30 degrees a value of theta that makes this true? Yes, so we have to include it. You could also put, if you wanted to, theta equals 30 degrees plus or minus 360 degrees n. You would have to say n is a whole number because you need to include the 0. And again, this is subtle, but when I say what are the angles coterminal with 30, 30 degrees is not coterminal with itself. So if you wrote down what are the angles coterminal with 30, you would not include the 30 degrees. But if I say what are the angles that make this true, 30 degrees is an angle that makes it true, so I have to include 30. The 0 included in the integer number set makes that happen, and the 0 in the whole numbers makes it happen. But you couldn't put natural here. Incidentally, is it clear why I don't need to put plus or minus up here? It's because the integers are positive or negative. Okay, but that's only one of them. The other one would be theta equals 150 degrees plus or minus 360n, where n is an element of the whole numbers. I'm choosing to write this as my answer. I'm choosing to go with the whole numbers. You could write them both with the integer notation. It doesn't matter. What matters is you understand. In other words, I could have also written 150 degrees plus 360 degrees n, where n is an integer, but I chose to go with the whole numbers. Any questions with E? Okay. So what we've actually done here is we've solved this equation. This equation, sine of theta equals 1/2, has a solution, and the solution is in the box. Do you understand, though, that I told you these two numbers right at the beginning? You didn't have to find them? Okay. Well, I'm not going to tell them to you from now on. I'm going to tell you, all right, solve this equation, and your first step is going to be to find these numbers so that you can write out a general solution. And you did this last year in Math 20. It's going to be a little different because we have more trigonometric ratios to work with. Warm-up number 2. On the grid below, put positive or negative in each blank. I always hesitate in going through this. I really do, but it seems every semester there are a couple of students that require this in order for them to be successful. So I don't want to leave anybody behind here. Let me just go through what it is we're doing, and then I'll explain why we're doing it. is sine of theta in quadrant 1 positive or negative? Now, in my mind, you shouldn't need to think very long or hard about that question. In quadrant 1, sine of theta will be positive because in quadrant 1, y is positive and r is always positive. So positive over positive gives you positive. You know, for the same set of reasons, everything in quadrant 1 is positive because in quadrant 1, both x and y are positive. And of course, r is always positive. And I would say that the people who need this don't need it for quadrant 1, but they may need it for the other quadrants. Let me just ask you this question, by a show of hands with a little bit of thought, without even looking at this. How many of you understand that, for example, in quadrant 2, cosine is going to be negative, sine will be positive, and tangent will be negative? That's the whole point. I think what you're doing when you say that, and we'll finish this off now, is that in quadrant 2, x is negative, but in quadrant 2, y is positive, and of course, r is always positive. So I don't know. When I said in quadrant 2, cosine is negative, how many of you thought, well, cosine is x over r, and x is negative there? I mean, that's kind of what we're talking about, but this is going to culminate with a rule that some people, as I said, need. So in quadrant 2, sine is positive, cosine is negative, and tangent is negative. Using the same reasoning here, in quadrant 3, tangent will be positive because both x and y are negative. And just for completeness sake, I'm going to put these negatives down here. R is always positive. And in quadrant 3, the coordinates are each of the two halves of the coordinate pair are negative, which makes cosine and sine both negative. Are you guys with me on this? Okay. We can do the same thing here in quadrant 4. I would say with just a small amount of thought, you should understand that in quadrant 4, cosine will be positive and sine will be negative, and tangent will be negative. R is always positive. Over here in quadrant 4, x is positive. But in quadrant 4, y is negative. Which means, and I never really said this, but I thought it was obvious, but maybe not. The reason why I'm going to put negative here is because any negative divided by a positive is negative, right? And this is positive, and this is negative. So I have a question for you. How many of you are no further ahead by doing that exercise? In other words, if I hadn't had it in there, it wouldn't have made a difference. Probably almost everybody. But there may be somebody who will benefit from this. And you're taught this last year. It's called the cast rule. How many of you remember that? I don't like it because it spells the word is cast, and the letters are spelt in the right order, but you don't start in quadrant 1. Does anybody remember what these letters tell us? You do, Ashira?
Which one of those will be positive?
Right, it tells you which of the 3 primary trigonometric ratios are positive. So in quadrant 4, only cosine is. They're all positive. Only sine is in quadrant 2, and quadrant 3 only tangent is. The problem I have with it is now we have 6 trigonometric ratios. So if I say to you, where is secant positive or negative? I wouldn't do this. I would just say secant is the reciprocal of cosine, and cosine is negative where x is negative, so it's over here. Right? I don't think you need a rule. If you do want to use this rule and you want something which starts in quadrant 1, has anybody told you what it would be for what you say? Add sugar to coffee. And some people will need that. Okay, everybody thinks a little bit differently. So let's get to it now. We're going to solve equations. So Would you agree if I say solve cos of theta equals 0.5242 from 0 to 2 pi, that what I am telling you is I'm looking for locations, and I can talk about the unit circle here. I'm looking for locations where on the unit circle I'm looking for locations where x is 0.5240. Yes? How many places will there be? 2. So between 0 and 2 pi, there are 2 angles. And we can even draw them here. There will be one that will be, well, approximately here. I can draw in my arc. Approximately here. And one, we'll draw in an arc down here, that will be approximately here. And I'm going to really dig down deep with this and give you a deeper explanation than you might have seen in Math 20. So I'm starting off with knowing that on the unit circle, cosine is the x-coordinate. So I'm visualizing the unit circle, and I'm saying there would be 2 places where the x-coordinate would be approximately 0.52. And now what I'm going to do is I'm going to label these. This is theta, and this is theta. And what we are after is the values of theta. That's the setup. What's the play? Well, the play is the first thing you do is you find the reference angle. And we haven't talked about reference angles this year, but I will remind you that reference angles are the smallest angle between the x-axis and the terminal arm, wherever that arm is. So in my diagrams, this is the reference angle, and this is the reference angle. And I want you to pay careful attention to this. I would have mentioned it in my Math 20 classes. Notice that the rotation angle, theta, has an arrow on the end of the arc. This is important. There's an arrow here. It shows a direction of rotation. There is an arrow here. It shows a direction of rotation. I don't draw arrows on my reference angle because it's not a directional thing. It's just an angle. Just how many radians it is between those 2 lines. So how do we find the reference angle? Does anybody remember? You take the inverse cos. Your calculator will give you the reference angle if you go inverse cos. So the reference angle will be the inverse cosine of 0.524. Now here's a problem though. If you look up here for a minute, and I go inverse cos of 0.5240, I get something which seems very reasonable, 58 degrees. I look at that and I go, yeah, that makes sense. But we don't want answers in degrees. We want them in radians because of this statement of the domain being from 0 to 2 pi. Now, I do not recommend, in fact, I would hope that you don't do this. Don't get your answers in radians and in degrees and convert them to radians. Just do what I just did, but do it with your calculator in radians. There is a bit of an issue here because when I hit equals, I'm going to get the reference angle in radians, and it will not be something that I understand too well. I mean, unless I remember that 1 radian is about 60 degrees. So what I'm getting is almost 1 radian, a little bit more. The reference angle here is 1.019 rads. I don't need to write the word rad because without any unit it's radians by definition, but I like to put it anyway. Now, how does that help us? Well, the rest of it is really simple because this reference angle is 1.019 rads. This reference angle is 1.019 rads. I hope it's clear, and I tend to use these colors all the time. I use red for theta, which is the angle in the equation, the rotation angle. I use red. I use green for reference angles. I hope it's clear here that this rotation angle for my first situation will be equal to 1.019 rads. This goes back to Math 20, where in quadrant 1, whatever the rotation angle is, that will be the reference angle. I hope it's clear that this rotation angle is going to be a full revolution minus the reference angle. Well, a full revolution is 2 pi minus that 1.019. And that is the number of radians of the second rotation angle. Now, what were we asked? Just look carefully here. It says to the nearest tenth. So what we would put for answers is that theta in between 0 and 2 pi is 1.0 rads. And we have to figure this out. This literally means pi is not a variable, it's a number. It means take 2 times pi minus 1.019. And you're going to get 5.2-ish. 5.26. So it would round to the nearest tenth to 5.3. I do want to just show that to you. So if I take 2 pi and I subtract that reference angle, I get 5.26, which is 5.3 to the nearest tenth. Okay? So the only thing that's different about this question is we're working in radians. You knew how to do this last year. You may not remember doing it last year, but you did. Okay? Cosecant equals negative 1.6588. Well, we want to first of all here change this to a primary trigonometric equation. This is an equation we're trying to solve for theta. It's trigonometric. So what I do, and this can get really tricky. Cosecant of theta is the reciprocal of sine of theta, which means that sine of theta is the reciprocal of cosecant of theta. And I know that some of you are algebra hounds. Like, you want to do things with algebra. And I think if you start to algebraically justify what you're doing here, you can psych yourself out. Okay? Sine of theta is the reciprocal of whatever cosecant is, which means sine of theta is the reciprocal of negative 1.6588. I mean, you can justify it algebraically, but I just find people get confused by it. Now, do you agree? I'm going to rewrite this. Do you agree that this thing that sine of theta is equal to is just a number? We don't need to figure out what negative 1 divided by 1.6588 is, because whatever it is, we're going to take the inverse sine of it to find the reference angle. However, I did just misspeak. We're going to find the reference angle. We're going to find the reference angle by taking the inverse sine of 1 over 1.6588. Not negative 1 over 1.6588. Please, you need to remember, when you find a reference angle, even if the trigonometric ratio was negative, you don't include the negative. The way the calculators are programmed, if you did, sometimes you'll get the reference angle, sometimes you won't. And where you go from there, if you use the negative, is a different road if it's sine, which is a different road than if it's cosine, which is a different road than if it's tangent. So I've always just had the philosophy, why would I teach you 3 different sets of rules when I can do it one way? Okay. So we're going to find the reference angle. Let's take a look at the question. Oh, degrees at least. We're in familiar territory. So the reference angle will be, don't forget to change into degrees, inverse sine of whatever 1 over 1.6588 is. And just to look up here for a second, look, you could have said negative 1 divided by 1.6588, and then said, okay, I need to take the inverse sine of 0.602. Do you see the problem here? I got to get rid of the negative, and I got to use all the decimals. Why not just get rid of the negative and put the number in as a fraction of 1 over that? I'm not going to get, oh, I forgot to go inverse sine anyway. Right. You know, just with that, I don't quite get the exact same answer. I'm going to go with the 37.07 degrees. So the reference angle is 37.07 degrees. And now, I'm going to ask you, I'm doing this in a different order than I did the first one. Where, in terms of quadrants, will cosecant be negative? Well, cosecant will be negative wherever sine is negative, because they're reciprocals of each other. Reciprocating a number doesn't change it from negative to positive. It's still negative. So where is sine negative? I don't use the cast rule. Sine is connected to y. It's negative down here in quadrant 3 and 4. So all we have to do to finish the question is do a little sketch of this reference angle in quadrant 3, and another sketch of this reference angle in quadrant 4. Notice again, I don't put arrows on there. And then the rotation angle will be this and that. Finding those two rotation angles is child's play. You're simply going to take, for the first one that is in quadrant 3, you're going to take 180 plus the reference angle. And for the one that's in quadrant 4, you're going to take 360 minus. I feel as though I don't even want to show my work here. We want to the nearest tenth, and this was 37.1, no, 37.0. So 180 plus 37.0 is 217.0. Am I right? 217? Okay.
And then 0.1 with rounding. Because I carried all the decimals.
Does it? Anybody else for rounding to 0.1? Okay. Oh, I know. I was looking at the one where I just had an approximate. Right, it's 37.07. Yeah, okay. And over here, you're going to go 360 minus that, which is going to give you 322.9. Still good? This is the lesson. This is it. There's one more layer at the very end, but that's pretty much it. So this one is just, you know, there's a little extra step here. A said cos of theta equals a number. It was ready to go into your calculator to find a reference angle. B was basically ready to go into your calculator to find a reference angle. You had to flip something over. C is not. But, geez, it's just pretty simple. You go tan of theta equals negative root 3. We want exact values. Okay, so if you were ever asked to determine exact values, it's because the angles that are the solutions will be those special angles on the unit circle. But I'm telling you right now, please do not try to wrap your head around where tangent has a certain value. You could probably do it, many of you, but if it's sine or cosine, it's easy to find because you're looking at y coordinates and x coordinates. Just use your calculator. But here's a tip. See this? Radians, right? Let's find a reference angle. Tan of theta equal, theta reference equals the inverse tan of root 3, correct? Okay, so if you want it in radians, inverse tan of root 3 in radians is an unrecognized, I know what that is, by the way, okay, but don't worry about it, is an unrecognized exact value of radians. I can tell you it's pi over 3. But you can't tell by looking at that. So what you do, even if it's a written response question, is you say theta reference equals, and you put your calculator in degrees so that you will recognize the reference angle. And what's going to happen here, when I repeat the calculation, is it gives me 60 degrees, and I go, oh, okay, pi over 3. Nobody needs to know how you go from here to that statement. But you need to write that you're finding a reference angle. If you don't, and I don't know, is there anybody, maybe, who could figure out that it's the 60-degree angle that would give you tangent equals root 3? If there is, you need to draw a diagram showing that and explaining it. And I think this is easier. Which two quadrants? Which two quadrants are we going to draw the reference angle in? Well, tangent is negative. Here and here. Quadrant 2, because tangent is y over x. So in quadrant 2, y is positive, x is negative. Divide, you get a negative. In quadrant 4, x is positive, y is negative. Divide, you get a negative. So it's in quadrant 2 and 4. Quadrant 2, this is pi over 3. The reference angle is pi over 3. And then quadrant 4, I tend to draw my pi over 3s bigger than they actually probably should be drawn. I just don't want you to confuse these points or arms with the 45-degree ones. I would really hope that you know that that's 2 pi over 3. I think if you have to go, oh, it's pi minus pi over 3 and start working with common denominators, you're in trouble. If you look at my arm, this is 0, 1 pi over 3, 2 pi over 3, 3 pi over 3. Over here, I would count this off as 1, 2, 3, 4, 5 pi over 3. That's how I would count it off. So theta equals 2 pi over 3 and theta equals 5 pi over 3. Any questions with C? I feel as though I'm going slow, but maybe I want to. Okay. 2 sine theta equals, pardon me, 2 sine theta minus root 3 equals 0 as exact values from 0 to 360. Well, 2 sine theta equals root 3. Sine theta equals root 3 over 2. How many of you can solve this without a calculator? I hope everybody. I hope everybody. Because sine is y on the unit circle, where is y equal to root 3 over 2? No reference angle needed. If I were to draw a circle, that's not bad. And I know that on the unit circle, this is 1. And I know a little bit about the unit circle, which is that when you have one of the halves of the coordinate pair being root 3 over 2, the other is a half or negative a half, it doesn't take me very long to realize that we are talking about this location and this location. I'm not even going to draw the terminal arms or show the rotation angles. I know that this is 1/2 root 3 over 2. This is negative 1/2 root 3 over 2. So how do I get to this first solution? Pi over 3. How do I get to the second solution? 2 pi over 3. I mean, there's nothing really to do here. Well, I better be careful about saying that. If this happens to be, you're doing a written response question that's maybe quadratic, and this is one of the results, and you just go from here to here, you'd better draw a diagram and label the points and explain. But here's the good news, at least for the time being. If this doesn't make sense to you, this looks like some kind of weird face. If this doesn't make sense to you, or you can't handle that, then you can do it the way we did the other ones, right? If sine of theta is root 3 over 2, and I just realized something. We wanted answers in degrees, didn't we? So it should be 60 and 120. Okay. We could do this. Use your calculator to find the reference angle. Put it in degrees. Regardless of what final answers you want, put it in degrees so you recognize it. I'm really hopeful that most of you understand it's going to tell you 60 degrees. Go ahead and find the reference angle on your calculator. You'll get 60. Where is sine of theta positive? In quadrant 1 and quadrant 2. So here is the 60 degrees. Here is the reference angle of 60 degrees. So what's the rotation angle? 120 and 60. I mean, you can still do it that way. Starting soon, a little bit next week and also in the next unit, this falls apart. You got to rely more on the unit circle. E, tan of theta minus 2 equals 0. Holy smokes, look at that domain. This is where things get a little ugly, okay? So this means tan of theta equals 2. I think you understand, but I will say it anyway. As soon as you see this, it's got to be the case that it's because these angles are not special angles. So we have to use our calculator. So let's find the reference angle. We're not going to recognize it in degrees or radians. It's not going to be a recognizable angle. In your radian mode, find the inverse tan of 2. .11 rads. Let's not worry, everybody, about that weird domain. Let's imagine, just for the time being, that what we actually want is from 0 to 2 pi. Don't worry about that. We'll get back to that in a second. But you know how to do this. You draw this reference angle in whichever two quadrants tangent is positive. Right? Tangent is positive. Where is tangent positive? It is positive in quadrant 1 and 3. So, as he draws it in quadrant 2. It is positive in this quadrant, so this would be 1.1 rads. Positive in this quadrant, it's 1.1 rads. And what I'm going to ask us to do is find the solutions for this domain, 0 to 2 pi. I'll pull this other domain in a second. What I want everybody to do is find this rotation angle and this rotation angle. Well, this one is simply 1.1 rads. What is this one? It's pi plus 1.1. 4.2. Can I get more decimals though?
How many do you want?
2.
4.25.
4.25. Does it round up to the 5?
Yeah.
Okay. So this is 4.25 rads. And because of the way what you just told me, if we end up rounding it to 1 decimal, we'd probably put 2 because it was a 4. But I don't care about that. So now, and this is what I want you to do anytime you see a goofball domain, not 0 to 2 pi, but something like this. I want you to draw a number line with these numbers on it. I want a number line down on paper that shows negative 3 pi over 2 to 2 pi. And I want you to figure out what those numbers are in approximate decimal form. We know 2 pi, well, I know 2 pi, it's 6.28-ish. Negative 3 pi over 2, I'd have to think about, so maybe you can tell me.
Negative 4.7.
Negative 4.7 pi. Okay. Now, you need to listen carefully here. These are the only 2 locations that make this equation true, right? But this location can be arrived at by going 1.1 rads, or adding a full revolution, or adding 8 full revolutions, or taking away a full revolution. Are you with me? Is this 1.1 rads, which is a solution to this equation, is 1.1 in this domain on the number line? Yes, 1.1 would be, I don't know, someplace over here. This would be where 1.1 is. It's inside of that domain. So I'm going to now make an official list at the bottom. Theta equals 1.1 rads. Now, if I add 2 pi to 1.1, it will still be that same location. So I do that, I go, let's see. 2 pi plus 1.1, I figure that out, and I get 7.4-ish. Is 7.4 in this domain? No. So this is not a solution. I hope you understand that we're not going to add another 2 pi in the hopes that if we add another 2 pi, we will get a number that's in there. And this is why I think the number line is a good visual. When we move to the right from 1.1 to coterminal solutions, we break the bank here. We go outside of the fence. But what about if I take 1.1 and I subtract 2 pi, which would be this angle, by the way. If I take 1.1 minus 2 pi, I get negative 5.18, I think. So I go negative 5.18. I swing my eyes over here and I go, nope, negative 5.18 is also going to be outside. So there is only one solution that lands in this position that's in that domain. We're done with the 1.1 now. What about 4.25? Is 4.25 in that domain? Definitely. It's less than 6.28, and it's definitely more than negative 4.7. So we can add it to our list. Pretty clear, obviously, I think. If we add 2 pi to that, we will be past 2 pi. There's no sense us adding 2 pi to this to see if we're still in the domain. But what if I take 4.25 and I take away 2 pi? You get negative 2.03, I think. Oh, that's in there. Negative 2.03 is someplace over here. So we add it to our list of solutions. If I subtract 2 pi again, is it clear that I will be past negative 4.7 in the leftward direction? These are my solutions. Anytime you get this awkward domain, you have to do that. You don't have to. I'm recommending it. I think you get the idea. No, we have time to do this. The first thing I'm going to do is rearrange this for secant of theta. Then what I'm going to do is write it in terms of cosine of theta. Oh, we're in degrees. Easier to work with. Any questions on the first two steps? Subtract 9, divide by 5, take the reciprocal and write it as cosine. Can everybody please find the reference angle, which will be the inverse cosine of 5/9, and let's just round it to the nearest tenth right away.
56.3.
56.3 degrees. We would want to sketch 56.3 in quadrant 1 and in quadrant 4. Nope. We would want to sketch that reference angle in quadrant 2 and quadrant 3. I made a mistake here. Let me explain it to you. And this is very rare for this to happen with me, but I can see how it would happen. Is I just looked over here and I saw 5/9, which is positive, I said. And right away I'm off the rails because I should be looking up here. Cosine is negative, which is quadrant 2 and 3. So if this is 56, and this is 56, what are the rotation angles? I'm going to use the 56.3. I will get I believe 123.7 by taking 180 minus the 56.3. Pretty sure that's right. And over here, I'm going to take 180 plus 56.3, which gives me 236.3. I think you could finish this question without a number line, but I'm going to put the number line anyway. We do not want from 0 to 360, even though that's what I did. We want from negative 180 to 180. Let's start with the 123.7. Is 123.7 degrees in this domain? Yes. So theta equals, I'm going to make my official list now, 123.7 degrees. How many of you are quite sure, just looking at this number line and the fact that this is 123.7, that if you add 360 to that, you will be outside of the domain, and if you subtract 360, you're going to be outside of the domain. The domain is only 360 wide, so wherever you are, if you subtract or add 360, you'll be outside. Is 236 points, yeah, of course. Is 236.3 degrees in that domain? No. But does that mean it doesn't have any solutions associated with it? No. 236 is over here someplace. What if we subtract 360? Will it put us in this domain? So you're going to go 236 minus 360, which will give you 123.7. Negative 123.7. And then if you subtract 360 again, you're outside of the domain. There's one little tiny thing, and it's so obvious I feel as though I don't need to teach it, but I will. Before I do, however, does anybody have any questions with that last example? Okay. You remember at the beginning? I never told you this is what we were doing, but we were solving this equation, sine of theta equals 1/2, and we discovered it was 30 degrees and 150. But then I said, what's the general solution? We simply added multiples of 360. Well, that's what this last thing is asking us to do. It's saying the general solution is a statement that includes all angles. So for A, B, C, and D in the previous question, what would the general solution be? No need to flip back. If you look at the two solutions for D from 0 to 360, we decided it was 60 and 120. So what's the general solution? I like the integer thing. I like not having to write plus or minus. That's it. That's all you have to do for any specific solution to get a general solution. Right? This would also be plus 360n, where n is an element of an integer. I'm normally not lazy. Really, I'm not. But, you know, Friday and all that. Yep.
It does say coterminal angles.
What's your point?
It could be 0 then, right?
Well, no, I guess maybe I should change that. I'm saying it's identical in nature to writing a general statement describing all coterminal. I'm not saying we only want coterminal. 30 degrees, not 30, 60 degrees and 120 degrees here are still solutions. I'm just saying I should change the word identical. I should have said this is similar to what we did when we wrote coterminal angles, but we do need to include the 0. And over here, what are we going to put? Plus multiples of 2 pi, because this is in radians. So here we would write plus 2 pi n plus 2 pi n, where n is an integer. That's laziness now. I'll let you fill that in. I mean, I think you get the idea, right? The general solution is a solution over the domain of all real numbers for theta or x or whatever the variable is, whereas the specific solution is typically from 0 to 2 pi. You need to be really solid with solving these equations. Because, whenever I say this, I know that it kind of scares some of you, but my motivation is to motivate you. Because when we get to a quadratic, you're going to have a whole bunch of work to do first to turn a quadratic into 2 of these that we learned today. So if solving one of these takes you 5 minutes, then solving a quadratic is going to take you 15, because you have to do some work first, then you'll have 2 of these to do. Okay. Try to rely on the unit circle if you can, or if you're capable of, and if it's possible. But if the angles are not common angles, you have to go to the calculator. Variety of questions solving what I call basic trigonometric equations.